We're using applications of differential equations, and my suggestion is to have your class examples handy as we do this. So in question 1, if we are putting a bottle of soda into the refrigerator, it's going to follow Newton's law of heating or cooling. So the change in temperature, if we use capital T for temperature, with respect to time, small letter t for temperature. Always a problem here with variables that both start with the same letter. So we can decide here whether we're going to use minutes or hours here for the time. So maybe we'll come back and see what units we want to put there as we talk about this. So Newton's law of cooling says the change in temperature with respect to time is directly proportional to the difference between the temperature and the surroundings. So this is a constant. This is the constant, not a variable, temp of the surroundings. So in this case, this is going to be the temperature of the refrigerator, which is going to stay at 44. So we know this is only a model. It's not the temperature of the soda actually will change the temperature of the refrigerator, but only slightly. All right, let's remember what we did in class. We separated the variables. Remember that S is not a variable. So we can put this with the dt, capital T, and we can move the small dt to this side, and we can integrate. So we have the natural log of this, which doesn't have a chain rule. The chain rule would just be a 1, so no problem there. And on this side, k is a constant, so this would give us a kt plus a c1. And then remember how we solve this. We exponentiate both sides. E to the natural log would just be this t minus s. And on this side, we would split this up. And remember that the e to the c1 becomes just another constant. And then we could move this s to the other side. The absolute value could be assumed in with the value of c, since c might be either positive or negative. So we might move the temperature of the surroundings over here. So now let's think what happens at time 0. At time 0, we would have e to the 0 power would just become 1. So our constant would be equal to t minus s. So C in each of these problems. So if you did a lot of Newton's law of cooling, you might just go right to this formula instead of deriving it over and over and over again. So we know what C is going to be in this specific example. All right, so what can we do here? In this case, we know that the temperature was 72 at time 0, and the refrigerator was 44. So in this case, our C value will be 28. So now we're getting closer to our model. We would have T is equal to 28. E to the KT plus the temperature of the surroundings was our 44-degree refrigerator. So our problem is still, what's this relative rate here? And that we need to plug in a specific value, and that's given to us here in the second sentence, after 1/2 hour. So this is where you have to choose. Are you going to use 30 minutes, or are you going to use hours and stick with 1/2? So I think I'll stay with time in hours. You could do the opposite. So I know that after 1/2 hour, our temperature is 61. So I could substitute this in for T. So I'd have 1/2 K. So we can find out the value of K. So let's subtract 44, and we'll have 17. And then can we divide by the 28 right away? And then you could write this as K over 2 if you wish. And then to solve for K, we'd take natural log of both sides. So we'll have k over 2, natural log of e, of course. I hope we're still not writing that. So our value of k would be 2 times the natural log of 17/28. And you can leave it that way, or you could round it off to a decimal value. So now we're still not finished quite with question A, but now we have our final model here. So we would have t is equal to 28e to the 2t ln of 17 over 28 plus 44. And we're asked to find the temperature after another half hour. So now we want to find out what is t when we put 1 in. So at time equals 1 hour. So our temperature, so grab your calculator, and t is equal to 1. So this is what we would want to calculate. And you can check to see if I have done all of these calculations correctly. But this is what I have in my notes. All right. And then next we need to find out how long will it take for the temperature to get to 50 degrees. So we're going to take our model that we've come up with. So we'll have this formula, and we want to find out when will t be equal to 50. So we could subtract the 44 right away, and we could divide by the 28 right away if we want to save a little writing space. So that would be 6 over 28, or of course 3 over 14 if you want to reduce that. And then we could take the natural log of both sides. So I'll just leave it as 6 over 28 so you remember where it came from. And on this side, that would bring our exponent down in front. And our ln of e is just going to become the 1 over on this side. So to figure out our time, we're going to, and you can clean this up, but why if we're just going to put it into our calculators? And I have approximately 1.544 hours. If you were working in minutes, I think that's about 92.614 minutes. All right, and now we're using our compound interest formula, and you should know these formulas for compounding a finite number of times. We have this formula, so we want to know the amount if we invest $10,000 at a rate of 4.5, so remember to change that to a decimal, compounded quarterly for 20 years. So in other words, this exponent tells you how many compoundings, how many times are you going to get interest. So the 4 times, oh, why did I put 80 there? 4 times 20 is 80. All right, so grab a calculator, and here, if it's a money question, to be safe, you could still use your 3 decimal places, but it's fine for the money problems to round to dollars and cents. And what if we had that same rate and we wanted to double our money? So we don't really care whether it was $10,000. You could put in $10,000 and then you would want $20,000 as your final amount. But you can see that it doesn't really matter what you put in. Whoops, sorry. Let's try getting back where I was there. Our interest rate. And then our NT. This time our T is our variable. And you can see that it doesn't matter whether it's $10,000 to $20,000 or whether it's $5 turning into $10, because you're going to divide. So if you want your money to double, you're simply going to put a 2 on this side. So it doesn't matter. Sometimes that confuses students when you're not told the amount of the investment. And that's because you're really just looking for that relative doubling. Your final balance is twice whatever your principal was. All right, so we're going to take natural logs of both sides. And then you're going to need your calculator. Our time value, we're going to divide by these. And just be careful about order of operations. And I have t of approximately 15.403 years. All right, question 3. We know that a cell divides into 2 cells every 20 minutes. So we could go right to our exponential population model, or let's, for sake of discussion here, let's repeat. If the population is proportional, the rate of change in the population is proportional to the current population, let's repeat the process of where all this came from. So if we divide both sides by p and multiply by dt and integrate, we had the natural log of the population is kt plus c1. And then when we did our exponentiation, the population was c e to the kt. So you could start right there. We know that model. And here what we know is that every 20 minutes, or every 1/3 of an hour if you prefer, our population is going to double. So at 1/3 of an hour, we would have twice the population that we had to start out with. So we started with a culture of 60, so we ended up with 120. So our C value, remember, is our initial population. C is equal to our initial population. So now we can find out what K is using this. So we take natural log. So our K value, sorry, and I didn't plug in what T is here. That was after 1/3 of an hour. Sorry. So in other words, K over 3 here. So our K value, since this is 1, our K value is 3 ln of 2. All right, so now we've got our model. So now we know that our population is equal to our initial population, e to the 3 ln of 2 times t. All right, or we can think about what happens here when we, another way of writing this, what is e to the ln of 2? Another way of writing this would be 60 times 2 to the 3t power. So those would be equivalent versions of the same equation. So with practice, you could go right perhaps to that answer, since we knew that we had a doubling function here. All right, so find an expression for the number of cells after 5 hours. So we want to take either version of these formulas, and it just doesn't matter which of these two you prefer, and we want to put 5 hours in for t. And I have 1,966, 080. I don't know. My notes are from a while ago. I guess that looks reasonable. Find the number of cells after 8 hours. So repeat that same process. And think what's happening here with this doubling. Every 20 minutes, so 3 times an hour it doubles. So our population should be getting significantly larger, and indeed it certainly has. These would be in the number of cells, by the way. And our rate of growth after 8 hours. All right, now let's think about this. Not the K value. This doesn't say relative rate of growth. This says our rate of growth after 8 hours. So we already found our answer for the population size. So the rate of growth is our dp dt. And we knew that that was equal to K times the current population. And we found out what K was. K was our value up above. Look at our K value, 3 ln of 2. Let's talk about that, by the way. What can we do with 3 ln of 2 here? That would be the natural log of 2 to the third, so you could also call that the natural log of 8. Okay, so natural log of 8 might be a simple way of saving yourself some calculation. And our population at time t, our population at 8 hours, we had just done up above. So take your previous answer in your calculator and multiply it by the natural log of 8. And we have to make sure we label our answer correctly here. Approximately 2,093, 234, 394.250 bacterium cells per hour. All right, so if you're using minutes, you make sure you label it appropriately. You'll have different values there. And when will the population reach 20,000 cells? So let's go back to our previous model. So here are 3 ln of 2. You could write again as ln of 8 if you wish, same thing. So let's divide both sides by 60. So we could, and you could of course make that 1,000 over 3. You can do as much simplifying as you wish here. And then we'd do our natural log of both sides. If I skip some steps here, natural log of E. So we would want to calculate, and of course simplify that as much as you wish. So if you had written 1,000 over 3 or some other equivalent value, and T is approximately 2.794 hours. All right, so hopefully these exponential problems are getting easier and easier for you.